Most electronic circuits cannot operate directly from the alternating voltage available at a wall outlet. They require a lower, stable direct voltage. A basic DC power supply performs this conversion in a sequence of stages. In India, the standard mains supply is approximately 230 volts at 50 Hz. This means that the voltage alternates between positive and negative values 50 times every second. Although this AC voltage is suitable for transmitting electrical power, it is not directly suitable for most electronic circuits. A basic DC power supply converts this AC input into a regulated and nearly constant DC output. The main stages are the transformer, rectifier, filter, and regulator. The regulated output is then delivered to the load. Let us follow the signal from left to right. We begin with the AC input. The waveform shown at the input is sinusoidal. It alternates above and below 0 volts, indicating that both its magnitude and polarity change continuously with time. This 230 volt, 50 Hz AC supply is applied to the primary winding of the transformer. The first major stage is the transformer. The main function of the transformer is to change the AC voltage level. In most electronic power supplies, it steps the mains voltage down to a safer and more suitable value. In some specialized applications, a transformer may step up the voltage instead. The amount by which the voltage changes depends on the turns ratio between the transformer's primary and secondary windings. Notice that the transformer output is still an alternating voltage. Its amplitude may be lower than the input, but its waveform continues to have positive and negative half cycles. Therefore, the transformer changes the voltage level, but it does not convert AC into DC. The transformer may also provide electrical isolation between the mains supply and the electronic circuit. This is an important safety feature. The transformer output is then applied to the rectifier. The rectifier converts the alternating voltage into a pulsating DC voltage. It uses diodes, which allow current to pass more easily in one direction than in the other. The waveform shown here represents half-wave rectification. During one half cycle of the AC input, the diode conducts and produces an output pulse. During the opposite half cycle, the diode blocks, and the output becomes 0. As a result, the voltage no longer changes polarity. However, it is still not a smooth or constant DC voltage. It consists of a series of positive pulses separated by gaps. The rectifier may be a half-wave rectifier or a full-wave rectifier. A full-wave rectifier uses both half cycles of the AC input and therefore produces a more continuous pulsating output. This makes filtering easier and improves the utilization of the input waveform. The pulsating DC output of the rectifier is next applied to the filter. The purpose of the filter is to reduce the fluctuations present in the rectified voltage. These unwanted variations are called ripple. A filter commonly uses a capacitor connected across the load. The capacitor charges when the rectifier output rises toward its peak value. When the rectifier voltage begins to fall, the capacitor discharges slowly through the load. In this way, the capacitor supplies current during the intervals when the rectifier output is low. The large gaps and variations in the rectified waveform are therefore reduced. Observe the filtered waveform. It remains positive and has a significant DC level, represented by VDC. However, small periodic variations are still present. The output is smoother than the rectified voltage, but it is not yet perfectly constant. The amount of ripple depends on factors such as the filter capacitance, the load current, and the rectification frequency. A larger capacitor generally produces less ripple, while larger load current tends to increase the ripple. The filtered voltage is then applied to the regulator. The regulator maintains the output at a nearly constant DC value. It compensates for variations in the input voltage and changes in the current drawn by the load. For example, the filtered voltage may vary because of ripple or fluctuations in the mains supply. The load current may also change when the connected circuit changes its operating condition. The regulator responds to these variations and keeps the output voltage stable. The regulated waveform is represented by a straight horizontal line. This indicates a constant DC voltage with practically no variation under normal operating conditions. The final stage is the load. The load is the electronic circuit or device connected to the power supply. It receives the regulated DC voltage and draws the current required for its operation. Examples of loads include amplifier circuits, microcontroller systems, communication circuits, and electronic instruments. Let us summarize the complete process. The AC input provides 230 volts at 50 Hz. The transformer changes the voltage level and provides isolation. The rectifier converts AC into pulsating DC. The filter reduces the ripple and produces a smoother DC voltage. The regulator maintains a stable output despite changes in the input or the load. Finally, the regulated voltage supplies the connected electronic circuit. The essential point is that each stage performs a specific function. Transformation changes the voltage level. Rectification makes the current unidirectional. Filtering smooths the voltage. Regulation keeps it constant. Together, these stages convert the mains AC supply into the safe, stable DC voltage required by electronic circuits.